Hello and welcome. In this video, we are going to go over how to evaluate properties using system state test steps. A thermodynamic state describes the thermodynamic equilibrium of a system using properties such as PT, V, U, H, S, etc. These properties are called thermodynamic properties. A system state is an extension of this thermodynamic state which adds other properties to make the state more useful to practical problem solving. Now, working substances, there is such a variety of that, are divided or classified into different thermodynamic models. And these models are covered in many different chapters. Chapter 0 and 1 introduce what is a state, and 3, 11, 12, and 14 covers different models. Because many other videos in this series will refer to this particular video, this is going to be a slightly longer video than others. So please bear with me as I go over some of the resources test offers for you to evaluate properties. But first, let's pin down what is a system state. We'll go to the property table. No, I'll go to the animations module and open up 1A system state. As I've already said, look at what is a system state, different layers of properties. It's describing state 1 or 2 system states shown in this animation. But look at how the properties are stacked. The material properties at the inner core and then the thermodynamic properties. So this is your thermodynamic state, and these are the layers we add to a system state, some extrinsic and some extensive variables, properties. Well, where do you find more information about the different models that we use? If you go to the property tables module, that's how you manually evaluate properties. For instance, you can find the superheated table by just clicking on that cell. If you click on a model cell right here, you can get a little more information about a particular model that makes it a model. What makes it a particular model is a set of assumptions that these materials belong to. And that's what we call, for instance, the SL model means solid or liquid model. A solid that remains solid throughout your problem, or a liquid that remains a liquid without changing phase. Similarly, the phase change model is probably is meant for PC model, means phase change model, when there's a possibility of a phase change, say water boiling into steam. Well, let's go to the test apps module, which is what we are after. So if you go to the states and system state branch, if you click there, you will see the different models again organized very nicely here. SL model that we already talked about is right here. So if you want to evaluate properties of a solid or liquid, this is the simplest model to use. Here is our PC model. And there are different gas models. You will find a ton of gas models here. The pure gas models are PG model, IG model, and RG model, means there's a single material here, nitrogen, oxygen, etc. The ideal gas model must be something you're familiar with, which obeys ideal gas equation of state. The PG model is a simplification of that, which assumes Cp and Cv to be constant. And the RG model uses generalized compressibility chart, which is not very accurate. It can even model a phase change fluid. So it should be used very carefully, with caution. The mixture models, as you can see, there's a pure binary mixture where there are two gases involved. Again, say you can solve nice complicated problem involving two different gases. The MA model is a special binary mixture. It's a moist air model. This is covered in chapter 12, by the way. And these are covered in chapter 3, all the other models that I have already circled. Finally, the general mixture of any number of gases, these guys are covered in chapter 11, and a gas which undergoes chemical reaction, chemical equilibrium is covered in chapter 14. All right, now that we have covered different models, let's launch a particular model and see what an app looks like. So let's say we launch the PG model test app. The default page you'll find is the hands-on example. You go to any test app, this is the tab, it will be the default by default shown, and you'll find elaborate examples. For instance, you'll find video solutions of different problems right here. Clicking here or here, you can see a particular problem being solved using this particular app. So we'll go to the app now by clicking on this tab. The default view is the state panel. As you can see, it's a collection of properties. As you move the pointer over any property, its definition appears at the bottom. The blue properties are the thermodynamic properties. The red ones are material properties. All the properties are color coded the same way as we saw in the animation before. To turn on a property, simply click on it. You don't have to click on the checkbox. So you can enter a value, but just to make sure, you can see that if you click on different properties, there is maximum number of properties you can click on. In a pure substance, in this case, 2 independent properties are sufficient. That's why you cannot enter more than 2 properties. Okay, so let's quickly calculate a state, an arbitrary state. So let's go back to this animation and make up a problem. Let's say we have air going from a certain temperature to another temperature so that the volume doubles. If initial conditions are given, we have to find what will be the final temperature so that the volume is say doubled or triple. Okay, so to make that, air is already the default fluid. Let's say the pressure is 100 kPa, and let's say the temperature initially is 300 Kelvin, and the volume is 1 meter cube. So just by hitting enter or the calculate button, the state is calculated. Let's say we have a second state, the final state. We have the same pressure. It's a constant pressure expansion, and let's say the volume became 3 times the initial volume. Of course, the mass of the air hasn't changed, so that's another information we know. Notice that now we cannot enter anything more. If I click and you will see that in the message panel it will say this is not an independent variable. A calculates this final state, and we found the final temperature. It's obvious. Volume became 3 times, so temperature became 3 times. If you go to the graphics panel, you'll see that the calculated states are described here, shown here graphically. If you draw a constant pressure line through state 1, obviously it must pass through 1 and 2. However, if you do a constant volume line from state 1, which is steeper, you can see how it works. These features of graphics panels are being propagated gradually over all the models. Finally, if you come here and click the super calculate button, what it does is it calculates all the states over again and produces test codes which can be used for different kind of purpose. It can be copied and pasted to something else or for later use to regenerate the solution. Also, super calculate button can be used for what if studies. For instance, suppose the pressure was not 100 kPa, but we put a big weight, and so the initial pressure was, let's say, 1000 kPa. So all we do is to recalculate state 1, and if I click super calculate, all the states are now connected, and we get the new answer. State 2 is found. In this case, the final temperature doesn't change, of course. It doesn't depend on the pressure, but other variables might. Anyway, let's go back to the original problem, and let's say I want to show you the usefulness of the test code very quickly. So we generate the test code, and we copy that and copy the test code here. Or we could just do Control A. That's easier, probably Control A, Control C. And let's say we want to see what will happen if we use the ideal gas model. So I'm starting a test step again, system state, and this time instead of PG model, we are launching the IG model. Again, everything is similar. We go, it almost looks identical, except the model is now ideal gas model. Cp and Cv are not constant anymore. In the IO panel, we go Control V, we paste the code and click the load button. And of course, everything gets recalculated. If you come here, you will see that the answer will not change because of the nature of the problem. But anyway, it shows that we can regenerate the solution very easily, or study what if the model changes using the test codes. Well, this is a made-up problem. Where do you find more problems on state evaluation? You go to the problems panel, problems module, and if you go to chapter 3, you will see a ton of problems on different models. You click on SL model, the section 3.2 is all about SL model. Similarly, PC model in section 3.3, etc. If you go to chapter 11, you will find the mixture model problems. If you click here, if you go to chapter 12, it's all about moist air, etc. In other words, also you will find a discussion link. If you click there, you can see what other, if there was any problems encountered by anyone else solving the problem, or if you're an educator, you can always go to the solution, and the test and manual solution will show up based on your access level. Well, I'll stop here and let you explore evaluation of properties using system state test steps.